So, okay, let's move on. In the last class, we began a new chapter, which was the chapter about symmetry, and we have gone through all of the symmetry elements and symmetry operations that there can be. And the last one that we discussed was a rotational reflection. It's a little bit more complicated than the other ones because they require two steps. And we have seen that we have to distinguish between rotational reflections that have an odd order and rotational reflections that have an even order. So we already discussed the odd order ones, and we have seen that we actually have to carry out the number of rotational reflections 2n times in order to achieve the identity. For those with even order, we only need to do it n times, and for that I would like to present an example here now. So a molecule that has an S4 rotational reflection is the methyl molecule. We saw that before. And you see here one improper rotational axis that actually bisects the two carbon-hydrogen bond angles. So now let us show that when we rotate reflect 4 times that we produce the identity. So now let us do this 1 time, then we carry out an S41 symmetry operation. We have to rotate counter clockwise by 90 degrees and then reflect. So that moves atom 1 from this position into that position. Okay, atom 2 from this position into that position, atom 3 from this position into that position, and atom 4 from this position here into that position over there. So now we need to do this a second time. Okay. Now when we do this a second time, then this is the same as just rotating by 180 degrees, because when we reflect 2 times, then that's as though we do not reflect at all. So in practice, we only rotate around 180 degrees as we go from here to here, not from here to here, okay? So now let's rotate reflect, starting out from here, carrying out the S4 2. So that means that we again have to rotate by 90 degrees counterclockwise and then reflect. So atom 1 moves from this position here to that position. Atom 2 moves from this position to that position. Atom 3 moves from this position to that position. Atom 4 moves from this position here to that position over there. Okay. Now we compare this molecule with this molecule over here, then we see that to go from here to here, we only need to rotate by 180 degrees around this axis here. Okay, so that means that in addition to the S4 axis, there also must be a C2 axis standing here. So that actually just swaps up these atoms, as you can see here, and these 2 atoms, as you can see here. All right. But now we have to do this operation 2 more times in order to produce the identity. So when we do it for the 3rd time, this atom 1 moves from here to here. This atom 2 moves from here to here. This atom 3 moves from this atom 3 here moves from this position to that position, and this atom 4 here moves from this position to that position. Okay. So now, last but not least, we have to carry out the operation the 4th time, and then we really produce the identity. We produce the original molecule. Okay, so atom 1 moves from this position into that position. Atom 2 moves from this position to that position. Atom 3 moves from this position to that position here. And atom 4 moves from this position into that position. Okay. So now from this, you can also see that you actually only have 2 independent symmetry operations associated with the symmetry element. This is the S41 and the S43, because the S42 can be expressed by the C21 and the S44 can be expressed by the identity. Okay, so now we have this fully discussed the symmetry elements and the symmetry operations that can exist in a molecule. So now let's ask what determines the overall symmetry of a molecule. And this is just the sum of the unique symmetry operations that exist within a molecule. So the sum of unique symmetry operations describes the overall symmetry of the molecule. Okay, so the overall symmetry of the molecule defines a so-called point group. So a point group is a mathematical concept. There's a mathematical theory which is called group theory. And within group theory, we know so-called point groups. And a point group is a group in which there is at least one invariant point. So this is the point that does not move when we carry out the symmetry operations. Okay? So because any molecule has a set of unique symmetry operations, any molecule and any object in general belongs to a point group. Okay? The number of the symmetry operations in a point group determines the order of the point group. It's called the order of the point group. Okay, so for instance, when a point group contains 5 symmetry operations, then the order of the point group is 5. If it contains 10, the order is 10, and so forth. So now in the following, let us go through all the possible point groups that they exist, and try to understand them and try to categorize them. And in order to do this, let's start here, this new presentation. And let's start with what is called the low symmetry point groups. So the low symmetry point groups, as the name says, has only few symmetry elements and few symmetry operations. So the lowest symmetry point group is called C subscript 1, and in this point group, the identity is the only symmetry element. It's called C subscript 1 because the identity is nothing else but, well, a rotational axis that has the order 1. So when we rotate around 360 degrees, it's as though we do not rotate at all. So this is where the name is coming from. So an example is this molecule here. So this is a bromochlorofluoro methane molecule. So the carbon is 4 substituents here. This molecule doesn't have a symmetry element other than the identity, so it belongs to the low symmetry point group C1. Okay, so what other low symmetry point groups do we know? In addition to that, there is CS. So in this case, we have one mirror plane in addition to the identity, but no other symmetry element and no other symmetry operation. An example for this is this ethene derived molecule here, in which from the regular ethene, 2 hydrogens are substituted by chloro and the bromo group, respectively. This molecule has a mirror plane, which is in the plane of the molecule, but no other symmetry element but the identity. So here again, we have an example in which the symmetry element, the mirror plane in this case, doesn't change the positions of the atom, but nonetheless that symmetry element exists because every point within the molecule is being mirrored from above the plane to below the plane and vice versa. So thirdly, there's this point group CI. So as the name says, in this case, we only have an inversion center in addition to the identity. Ci is sometimes also called S2 because an S2 symmetry operation is the same as an inversion. So an example is this molecule shown here. So this is a dibromodichloroethane in a staggered conformation. And this molecule looks relatively symmetric, but it has actually only an inversion center in addition to the identity. Where is this inversion center? This inversion center is here in the middle of the carbon-carbon bond. Okay, and we can move all the atoms through that inversion center to the other side. So that moves this bromine atom through the inversion center here to the other side. It moves this chlorine atom here through the inversion center to the other side. And it moves this hydrogen atom through the inversion center to the other side. And also the carbons are being swapped up by their movement through the inversion center. So these are all the low symmetry point groups, and the low symmetry point groups are pretty straightforward to understand because there are not so many symmetry elements. So on the opposite end, we have the so-called high symmetry point groups that contain a lot of symmetry elements and a lot of symmetry operations. So you can understand high symmetry point groups the easiest way, I believe, when you derive them from the concept of Platonic solids. So a Platonic solid is a polyhedron which is constructed from regular polygons in which all vertices, edges, and faces are equivalent from the standpoint of symmetry. So there are only 5 possibilities for so-called Platonic solids. So this is the tetrahedron, that's the octahedron, that's the cube, that's the dodecahedron, and it's the icosahedron. Okay? So the tetrahedron, the octahedron, and the icosahedron are being made from triangular faces. Okay, the tetrahedron, as the name says, has 4 triangular faces. The octahedron has 8 triangular faces, and the icosahedron has overall 20 triangular faces, hence the name icosa, which is the Greek prefix for 20. So in addition, we have the cube. So the cube is made of squares. Okay. So there are 6 squares that produce a cube. And a dodecahedron is made of pentagons. You see one of the pentagons here. So overall, you have 12 pentagons that make up this dodecahedron, and all the 12 pentagons are equivalent, and so are the edges, and so are the vertices of the dodecahedron. Okay, so let's go through all the Platonic solids step by step and see to which point groups they belong. So before we're doing that, I just wanted to point out that the icosahedron is probably the most complicated of the polyhedra to understand, but it can actually be studied even from the inside and outside. So when you actually go to Allentown Cedar Beach Park, there's a playground, and I've been there with my daughter, and I've seen that there's an icosahedron there. Okay, so you see here the triangular faces. Okay, and the triangular faces, they actually cap a pentagon here. Okay, and there are more triangular faces here and here. Okay, there are also triangular faces here in the front and here. Okay, and also here, for instance. So overall, that's a 20. So if we go to Allentown Cedar Beach Park, You can study an icosahedron not only from the outside, but also from the inside if you want. But this is, of course, completely optional. All right, but now let's go to the point groups associated with the Platonic solids. So the tetrahedron belongs to the point group TD, and a number of tetrahedral molecules, for instance, methane or tetrafluoroborate, also belong to the point group TD. So let us understand the point group TD using a regular tetrahedron. So when you determine symmetry elements and symmetry operations, it's useful to first see what is the principal axis. And the high symmetry point group have the property that they have multiple principal axes. Okay. So the axis with the highest order within a tetrahedron is the C3 axis. Okay. You see one C3 axis here. Okay. So now you see that, well, the C3 axis goes through one corner, one vertex of the tetrahedron, and also one face. Okay, now you can ask, how many C3 axes would you expect? Now consider that when you have a Platonic solid, all vertices, all edges, and all faces are equivalent. Okay, so now a tetrahedron has 4 vertices. Okay, so when one C3 axis goes for one vertex, how many C3 axes will we have? Well, we will have as many as we have vertices. So we have 1, 2, 3, 4. So therefore, I would expect 4 C3 axes. Okay, now you see them all here. The first one, second one, third one, and the fourth one, which we have already considered over there. Okay, so now how many symmetry operations are associated with these C3 axes? Well, we have to consider in principle all symmetry operations between C31 and C33. So C33 is the same as the identity, so we only need to consider C31 and C32. Okay, so because we have 4 C3 axes, we will have overall 8 operations. Okay, so 4 of them will be C31 and the other 4 of them will be C32. As mentioned previously, the C33 will already be accounted for by the identity. Okay, so next we can ask, well, what other axes, proper rotational axes, are there in addition to the principal axis? And there are C2 axes in addition to the C3 axes. So you see one here. Okay, so you see that such a C2 axis goes through the center of 2 edges. Okay, and as we carry out the symmetry operation, well, this will swap up, well, these 2 corners here and these 2 corners in the tetrahedron respectively, and after that our object will be indistinguishable from its original form. So now how many of these C2 axes will we have? So in this case, our C2 axis goes through the center of 2 edges. Okay, so in order to, well, calculate how many of these C2 axes we have, we can count the number of axes we have, divide that by 2, and that's our number. So how many edges does a tetrahedron have? Well, it has 1, 2, 3, 4, 5, 6 edges. So 6 over 2, that gives 3. Okay. So therefore we have 1, 2, 3 C2 axes. So now how many symmetry operations will be associated with the C2 axis? Well, in principle, we have to consider for each C2 axis, the C21 and the C22, but the C22 is all expressed by the identity. Therefore, we only consider the C21. So that means that we have 3 C2 symmetry operations, and all these C2 symmetry operations are C21 symmetry operations. So now we have considered the proper rotational axes. So next we can, for instance, ask, well, what improper rotational axes do we need to consider? As we have seen previously, a tetrahedron has S4 improper rotational axes. So where do they run? You see that they basically run where the C2 operations ran previously. So they go through 2 opposite edges. So then how many of these S4 symmetry elements will we have? Well, again, as many as we have edges divided by 2. So we said previously that we have 6 edges, so 6 over 2, that gives overall 3. So we have overall 3 of these S4. Here's one. Here's one. And there you see actually the third one going actually this way. You also see the respective associated mirror planes. Okay, so now how many symmetry operations do we have to consider overall? So each S4 axis is associated with 2 symmetry operations. The S41 and the S43, we have seen that already previously. So the S42 is the same as the C21, and the S44 is the same as the identity. Okay, so therefore for each S4 element, we have 2 operations. Okay, since we have 3 elements, we have 6 times 2 is equal to 6 S4 operations, and these are 3 S41 and 3 S43 operations. So next, we can look at the mirror planes. Okay, what regular mirror planes do we have? So you see one here. Okay. When we carry out the symmetry operation, well, we move basically every point which is here to the left, to the right, and from the right to the left. You can see that actually swaps up these 2 vertices of the tetrahedron. So these 2 vertices here, these 2, they do not change their position. Now these, so you see that this mirror plane here contains the principal axis. So you see the C3 axis here, or one of the C3 axes here. So that makes this mirror plane a vertical mirror plane. But now in addition, this mirror plane bisects the angle between 2 of the C2 axes, that is here and here respectively. And that makes the vertical mirror plane a dihedral mirror plane. So now how many of these dihedral mirror planes will we have? So we see that each of these mirror planes contains an edge. In this case, this is this edge here. Okay. So now how many edges do we have? Well, we have overall 1, 2, 3, 4, 5, 6 edges. So therefore we would expect 6 of these mirror planes. And now you see all of them here on the right side of the slide. So what are the symmetry operations associated with this mirror plane? So we know that each mirror plane is associated with 1 symmetry operation, because mirroring 2 times produces the identity. So therefore we have 6 operations, 6 sigma d operations. Okay. So what else? Well, there's no other symmetry element, so we do not have an inversion center to consider. Therefore, we have now found all the symmetry elements and all the symmetry operations. So we have 4 C3 axes. Okay, we have 3 C2s, we have 3 S4s, and we have 6 sigma d mirror planes. And these symmetry elements describe the overall symmetry of our tetrahedron and the point group TD. Okay, so here you have them now listed. All. Okay, that means that we have described now the tetrahedral point group TD. What other high symmetry point groups do we have? So first of all, there are so-called subgroups of the point group TD. So these subgroups have the symmetry elements of the point group TD except some. Okay, this is why these groups are called a subgroup. And the first group is the rotational subgroup T. So it's called rotational because all the symmetry elements, but the proper rotational axes are being eliminated from TD. Okay, so that leaves then still the 4C3. Okay, the 4C32 and the 3C2 symmetry operations, besides the identity, but all the other symmetry operations that exist for the TD point group are gone. So an example for this is this cage molecule here. So this cage molecule has 4 gallium atoms here that build a tetrahedron. And if you considered the arrangement of the gallium atoms only, well, the point group would be TD because we have a regular tetrahedron. However, these gallium centers are now linked by 6 of these ligands here. And now, due to the shape of these ligands and how these ligands coordinate to the gallium atoms, the symmetry is being reduced. So all the improper rotational axes and all the mirror planes are eliminated. Okay, so that the molecule is now in the point group T. Okay, so there's another rotational, so another subgroup, and I'm a little bit faster than expected today, but that doesn't matter. Can continue anyway. We just bring this up here. Now I need to switch my screen again so we can start now with the octahedral point group. So So there are two platonic solids that belong to the octahedral point group. So this is the octahedron, which you see here, and the cube. So these have quite different shapes. So the octahedron is made out of triangles, whereas the cube is made out of squares, but nonetheless, they belong to the same point group, OH. That means that they both have exactly the same symmetry elements and exactly the same symmetry operations. So a molecule that, for instance, has an octahedral shape is the SF6 that we have already previously discussed. Cubic molecules are far less common than octahedral ones, but there are some examples. You see here cubane, in which we have 8 carbon atoms shaped in a cube, and each carbon atom has an additional hydrogen atom. So the overall composition is C8H8. So now let us determine the symmetry elements and symmetry operations, just as we did for the tetrahedron. Now we could use either the cube or the octahedron to do this. The result would be the same. Let's just use the octahedron in order to do that. Our choice is arbitrary in this case. So let's first look where we can find the principal axes. And again, there are multiple principal axes to consider here because we have a high symmetry point group again. So you see here C4 axes, or one of them, that goes through two opposite corners of the octahedron. So we can ask, well, how many of these symmetry elements would we expect? Well, our octahedron has how many vertices? Well, it has 1, 2, 3, 4, 5, 6. Therefore, we would expect, well, 6 over 2 is equal to 3 C4 axes. So you see here actually in this animation how the C4 axis moves the atom also. So now you see now here the additional C4 axis. Okay, this was the original one. Then we have a second one here, and we have a third one going through these two opposite vertices. Okay, then in addition to these C4 axes, you have also C2 axes, and these C2 axes stand exactly where the C4 axes stand. Okay, so I have 3 C2s in addition to the 3 C4s. So how many symmetry operations will result? Well, for the C4 axis, in principle, you have to consider everything between the C4-1 and the C4-4 operation. But the C4-4 operation is the same as the identity, so you do not need to consider it. So in addition, you do not need to consider the C4-2, which rotates 2 times around 90 degrees. So rotating 2 times around 90 degrees is like rotating around 180 degrees, and rotating around 180 degrees is already accounted for by the associated C2-1 symmetry operation. Okay, so we do not want to count symmetry operations twice, and we tend to count the more simple symmetry element over the more complicated symmetry element. So we choose the C2-1 over the C4-2. So now how many operations do we have then overall? Well, there's still the C4-1 and the C4-3 left. So we have 2 operations per symmetry element. So we have overall 3 C4 axes, okay? So that gives overall 6 C4 symmetry operations, okay? 3 of them are C4-1 and 3 of them are C4-3. Okay, then we have this 3 C2 symmetry operations associated with the 3 C2 axes. So what other symmetry proper rotational axes do we have? So in addition to the C2 and the C4, we have C3 axes, and you see one of them here. You see that this C3 axis goes through 2 opposite faces of the octahedron. Okay, you see that these 2 faces, okay, are, well, oriented in a staggered fashion relative to each other. So as we carry out the symmetry operation, you see this here, yeah, we rotate our 20 degrees, and then this face, well, superimposes the original face, and this face here again superimposes the original face, and the entire octahedron superimposes. So how many of these C3 axes do we have? Well, you see that we have 1 C3 per 2 faces in this case. So the overall number of C3 axes should be the number of faces divided by 2. So how many faces does an octahedron have? It has, well, as the name says, 8 faces. So we should have 8 over 2 is equal to 4 C3 axes. Okay, and you see them all 4 here. So this is the first one that we saw already. Here is the second one. Here is the third one. And here is the fourth one. So now, how many symmetry operations are associated with these 4 C3 axes? So when we consider only one C3 axis, then in principle, we have to consider everything between C31 and C33. C33 is the same as the identity, so we only need to consider C31 and C32. So that gives 2 symmetry operations per symmetry element. We have 4 symmetry elements, so this gives 4 times 2 is 8 symmetry operations. 4 of them are the C31, and the other 4 are the C32. So now, are there still axes left that we have not considered thus far? And the answer is yes. So there are additional C2 axes to the C2 axes already identified. So the ones already identified, they ran in the same position as the principal axis. Okay, so therefore have the fewest number of primes. So any other C2 axes need to get primes. Okay, so you see here additional C2 axis that goes through 2 opposite vertices. 2 opposite edges. So this here is the first edge, and this here is the second edge. So now, as we carry out the symmetry operation, okay, our octahedron again rotates into an indistinguishable position. So now how many of these type of C2 axes would we have that are conjugate to each other? Well, we have to count the number of edges, divide that by 2, and that should give us the correct number. So let us count the number of edges. So we have 1, 2, 3, 4 here. We have 5, 6, 7, 8, 9, 10, 11, 12. So that means that we should have 12 over 2 is 6 of the C2 axes. Okay? So we have 6 C2 prime. So how many symmetry operations will there be associated with it? So for C2, we have as many operations as we have axes. So we have overall 6 C2 prime 1 symmetry operations. So now we are finished with our proper rotational axes. We can now pay our attention, for instance, to the mirror planes. So the octahedron has horizontal mirror planes, and due to the fact that there are multiple principal axes, there are also multiple horizontal mirror planes. Okay, so you see one horizontal mirror plane here, and you see that this horizontal mirror plane contains a square, one of the 3 squares which defines the octahedron. Okay, the first one is this one. Okay, and the second one is that one. And the third one is just this one. Okay, so now this mirror plane here stands perpendicular to the principal axis that actually stands here. Goes through these 2 opposite vertices, and that makes this mirror plane here a horizontal mirror plane. It stands horizontal to a principal axis. So note that it actually also contains a principal axis, which is here. So in a way, it has also properties of a vertical mirror plane, but the horizontal properties are considered to be dominating over the vertical ones in this formalism, so we consider them as horizontal mirror planes. So now as we carry out the symmetry operation, you can see our object becomes indistinguishable again. So how many of the horizontal mirror planes do we have to consider? Well, we need to have as many as we have principal axes. Okay, so we had 3 principal axes, so therefore we should have 3 of the horizontal mirror planes. And you see them now all 3 here. They go through the 3 squares which define the octahedron, as I said before. So this is the first one here. So this is the second one here. And that one here is the third one. Okay, so now how many symmetry operations are associated with this? Well, for each mirror plane, no matter if it's a horizontal or vertical mirror plane, we have only 1 operation associated with the mirror plane. So we will have 3 sigma h operations. Okay, so now do we also have vertical mirror planes in addition to the horizontal ones? And the answer is yes. And these vertical mirror planes, they bisect the octahedron this way. Okay, so in a way that is actually cutting 2 edges, 2 opposite edges of the tetrahedron in half. Okay, so these mirror planes, they only contain a principal axis as a C4, but they do not stand perpendicular to a principal axis. Okay, so in this case, this mirror plane here contains this C4 principal axis, but you see the other C4 principal axis here and here, okay, they do not stand perpendicular to this mirror plane here. So therefore, this kind of mirror plane has only the properties of vertical mirror planes, so we name them vertical mirror planes. So these mirror planes are even dihedral mirror planes because they bisect the angle between two of the C2 prime axes that we previously considered. Okay. You see that this angle here between these two C2 axes is bisected by this vertical mirror plane, and that makes this vertical mirror plane a dihedral mirror plane. So how many of these dihedral mirror planes will we have? Well, you see that each mirror plane contains a principal axis, and one of them only. So we have three of these principal axes, so we would expect that we have overall the same number of vertical mirror planes. And you have just seen through animation how the vertical mirror plane, the dihedral mirror plane to be more precise, transforms the octahedron. Okay? Oh no, I was wrong. There are 6. Why is this? No, I'm lost. I made a mistake. Sorry about that. Yeah, I know why. Because here only one of the two vertical mirror planes that contains this C4 is actually shown. So there's actually an additional mirror plane to this one here, okay, that stands perpendicular to this mirror plane. I don't know if you can see that. Okay, so it would actually go through these two opposite edges here. It would bisect these two opposite edges. And then that doubles the number of the dihedral mirror planes. Then we have not 3 dihedral mirror planes, but 6 dihedral mirror planes. So oversight on my side. So here you see all the 6 dihedral mirror planes that exist in addition to the 3 vertical mirror planes that we already considered. So how many symmetry operations do we have? Well, we have as many symmetry operations as we have symmetry elements. So we have also 6 sigma d symmetry operations. Okay, then in addition to that, we also have an inversion center in the middle of the octahedron. Okay, as we carry out the symmetry operation, okay, we move all the points through the inversion center to the other side. So we can only have one inversion center per object, and we can only have one symmetry operation associated with each inversion center. So now, in addition, we have to consider the improper rotational axes associated with the point group OH. So the one with the highest order is an S6 improper rotational axis. And that improper rotational axis goes to the center of a triangular face, and actually to the center of 2 opposite triangular faces. So it actually stands exactly where these 3 proper rotational axes are. So now carrying out the symmetry operation moves again the atoms into an indistinguishable form. Okay, so we first rotate by 60 degrees, and then we mirror perpendicular here at this mirror plane. So how many of these elements will we have? So each element contains actually 2 faces, these 2 opposite faces. So we previously saw that we have 8 faces to consider. So 8 over 2, that gives overall 4 symmetry elements. to consider. So how many symmetry operations will we have to consider? Well, in principle, we have to consider everything from S61 to S66. Okay, remember here we have an even number, but the S62, the S63, and the S64 can be expressed by simpler symmetry elements. So we have only the S61 and the S65 to consider. So overall, we have 8 symmetry elements to consider, given that we have 4 improper rotational reflection. So the S62 is equal to C31, the S63 is identical to the inversion, the S64 is identical to the C32, and the S66 is identical to the identity. So let us just finish this up. The octahedral point group has also an S4 symmetry operation. So these S4s stand where the C4s stand. So they go through 2 opposite corners. Okay, so as we carry out our symmetry operation, we rotate around 90 degrees and then we mirror perpendicular. Okay. So we had 3 C4s. So the S4s stand where the C4s are. So therefore, we must also have 3. So how many symmetry operations will we have? Well, for the S4, we have the S41 and the S43. The S44 is the identity, and the S42 is the same as a C2 prime. And therefore, we have, well, 3 times 2 is equal to 6 symmetry operations. And now we have found all the symmetry operations for the octahedral point group OH. And you see it's actually quite a lot of them. So these are all the symmetry elements here. And these are all the symmetry operations which are independent. So these here in parentheses are all the symmetry operations that can be expressed by simpler symmetry operations. So let us stop at this point. So I stop the recording.